Okay, so we studied the method of reflection for the extension of functions. We will now see how it can be used for general domains. Okay, we start with the definition. Let omega contained in Rn be an open set. We say that omega is of class Ck where k greater or equal to 1 is an integer if for every x in d omega there exists a neighborhood u of x in Rn and a map T from Q to U such that 1 T is a bijection, 2 T belongs to Ck of Q, T inverse belongs to Ck of U, and 3 T of Q plus equals U intersection omega and T of Q0 equals U intersection d omega, where Q is set of all x in omega in Rn such that x equals x dash xn mod x dash less than 1 mod xn less than 1. Q plus equals set of all x in Q such that xn is greater than 0, that is the upper half plane, and Q0 is set of all x in Q such that xn equal to 0. Okay. So remember, this is the picture. Q is this cylindrical domain. So this is x dash, which is Rn minus 1, and here you have xn. So Q plus is here, this is Q0, and the whole cube is called Q. So what do we mean by this? So if you have, this is the boundary of omega here, d omega, and omega is some set which is on this side. So for every x in d omega, you have a neighborhood u, and you have here q. Okay, and so you have here q plus, and this is q0. Okay, so you have a mapping T here, and you have, it takes q0 to the boundary. Okay, so that is what it does, and this is u intersection omega, the upper part here. Okay, so you have this mapping. So examples: open balls in Rn are in Ck for all k. So we say they are of class C infinity. So are complements of closed balls. A polygon is not even of class C1 since we cannot verify the above conditions at the vertices. So we say it is of class C0. Okay, so C infinity means it's in Ck for every k, and this is of class C0. Okay, so now we are going to prove an extension theorem. So before that we need the following technical lemma, another simple thing. So omega contained in Rn, open set, and u belong to W1p of omega, 1 less than or equal to p less than infinity. K contained in omega, a closed set, and if u vanishes outside K, then u tilde the extension by 0 outside omega is in W1p of R. So proof. So u tilde is of course in LP of Rn, no problem. So we only need to check the derivatives. So let phi belong to D of Rn. Let K1 be equal to K intersect support of phi, and this implies K1 contained in omega and it is compact. So it is a closed subset of a compact set. K is closed, support of phi is compact, so the intersection is compact. Okay. Now let psi belong to D of omega such that psi is identically 1 on K1. Now for 1 less than or equal to I less than or equal to n, you integral over Rn, u tilde d phi tilde, sorry, d phi by dxi equals integral on omega u d phi by dxi dx, and since u and phi, u vanishes outside K, phi vanishes outside the support of phi, and therefore this can be integral can be written over K1 u d phi by dxi, and psi is identically 1 on K1, so this is equal to integral on omega u u psi d phi by dxi dx, because psi is identically 1 on K1 and therefore this integral will be the same. Everything is 0 outside K1 and on K1 psi is 1 and therefore this integral is the same. So which we can write as integral u d by dxi of phi psi dx over omega minus the integral on omega u phi d psi by dxi. Now u is u and phi, they live inside K1 because u vanishes outside K, phi vanishes outside the support of phi, so u phi is, but on K1 this lives only in K1, and on K1 d psi by dxi is 0 because psi is identically 1 and therefore this integral vanishes. Okay, so you have that integral u tilde d phi by dxi is equal to minus integral omega, and of course you have phi psi belongs to d omega because phi is in d of Rn, psi is in d omega, and therefore by definition of the distribution derivative, this is minus du by dxi of phi psi dx, and of course this is phi psi, u and phi live only on k1, psi is equal to 1 on k1, and therefore once again we can write this as integral, we can drop the psi, so that is minus du by dxi of phi dx on omega, which is equal to minus integral over Rn du by dxi tilde phi dx. Consequently, du tilde by dxi is equal to du by dxi tilde, which is in LP of Rn, and that proves the theorem. All the function is in LP, derivatives are all in LP, and therefore you have the thing. So now we have the following theorem. Let omega contained in Rn be an open set of class C1. So we call the definition, there should be a mapping of T of type C1 which between Q and every boundary, okay, whose boundary is bounded. So it could either be a bounded open set or the complement of a bounded open set. Both of these cases will have a bounded boundary. Okay. So let 1 less than equal to p less than infinity, then there exists an extension operator p from W1 p of omega to W1 p of R. Since omega is of class C1, each x in d omega has a neighborhood u and a mapping T from Q to U as in definition. Okay. But d omega is compact, implies it can be covered by a finite number of such neighborhoods. So let us take, let d omega be contained in union j equals 1 to k uj, and let tj j equals 1 to k corresponding ck maps, c1 maps from q to uj. So tj goes from q to uj, so that tj inverse are class C1 in the respective domains, and then it maps Q0 into d omega in section 0 and so on and so forth. Okay. So consider the covering uj j equals 1 to k and Rn minus d omega. Of Rn. So this is only a finite cover of Rn, and therefore you do not have to worry about local finiteness. Let psi naught psi j equals 1 to k union psi naught be a partition of unity, C infinity partition of unity. I usually have to put the word locally finite, but now we only have a finite cover and therefore it does not matter, we do not have to use that word at all. Okay. So you have that support of psi j is contained in uj, and uj is a bounded set. Okay, so you, because it's the image of q, and therefore this is compact. So these are all compactly supported, and support of psi naught is contained in Rn minus d omega, and finally we have sigma j equals 0 to k psi j is identically equal to 1. So if u is in W1p of omega, you can write u equals sigma j equals 0 to k psi j u. So now psi 0 of u is supported away from d omega, and psi j are compactly supported, 1 less than equal to j less than equal to k. Okay, that we already saw. Okay, so deep psi naught by dxi is equal to minus sigma j equals 1 to k deep psi j by dxi. So implies derivatives of psi naught are bounded, are in L infinity of Rn, because all derivatives can be written in terms of psi j. Psi j's are compactly supported functions, so they have bounded derivatives. Okay, so this implies that psi naught of u belongs to W1p of omega, because its derivatives are all in L infinity. So by the product rule, d by dxi of this will be deep psi naught by dxi into u, which is in L infinity, plus psi naught du by dxi, that is also in L infinity, and therefore you have that is true, because sigma psi j is equal to 1, and all the psi j's of course are 0 less than equal to psi j less than equal to 1 for all g. Okay, so we also have that. And since it vanishes in a neighborhood of d omega, by the previous proposition, psi naught u tilde belongs to W1p of Rn. Clearly, norm psi naught tilde u in 1p Rn equals norm psi naught u in 1p omega, and that is less than equal to c times norm u in 1p omega LP, because the psi naught, everything is bounded, the derivatives are bounded, and therefore they will all be absorbed in this constant c, and therefore you have this. So okay, so now you let 1 less than equal to j less than equal to k. Okay, so you consider u restricted to uj intersection omega. So for y in q plus, so recall that q plus is mapped to u intersection omega, okay, and therefore you define Vj of y equals u of Tjy. So from q plus to this portion you have a mapping, and therefore you go there, you take u intersection omega, uj intersection omega, and then you have Vj of y, you have a function here. So now you can, easy to show that Vj belongs to W1p of q plus. So by reflection, Vj star belongs to W1p of Q. Then you define Wj of x equals Vj star of T inverse of y, T inverse of x for x in Uj. Then Wj again, because of since T inverse are all C1 functions, you have Wj belongs to W1p of Uj, and Wj equals U on Uj intersection omega, okay, and norm Wj, all these are the immediate consequences. 1p Uj is less than or equal to some constant Cj times norm U, 1 Uj intersection omega 1p Uj intersection omega, which is less than or equal to Cj norm U in 1p omega. Then psi j Wj is compactly supported in Uj, and so that implies that psi j Wj tilde belongs to 1p of Rn, the extension by 0, okay, and norm of psi j Uj Wj tilde in 1p Rn is less than or equal to therefore Cj times norm U 1p of omega, okay. So now you define U going to Pu, which is equal to definition psi naught U tilde plus sigma j equals 1 to k psi j U Wj tilde. So this belongs to, so Pu belongs to W1p Rn, Pu equals U on omega, and norm of Pu 1p Rn is less than some constant times norm U 1p omega. So you have P is an extension operator. Have a C1 domain, you can definitely extend it in this fashion, okay. Corollary, if omega is of class C1 with d omega bounded, then as usual C infinity omega intersection W1p omega is dense in W1p omega, because you take the prolongation, then you know that that can be approximated by d of Rn functions, and then you restrict it to omega, and because you have prolongation operator you do not have to use Friedrich's theorem, you have directly this thing. So this completes the extension theorem. Next we will study the spaces W1p 0 of omega, where the extension is very easy, and that leads to a very important inequality called Poincaré's inequality. We will see that next time.